Okay, so we should now have a firm grasp of what a polynomial is, how to graph a polynomial, and how they can behave. We know that we can add two polynomials and subtract two polynomials and multiply two polynomials together, and you'll still get a polynomial. But when you divide two polynomials, you get a new type of function. So as an example, if I divided x squared minus 3x plus 2 divided by x squared plus 2x minus 3, as I have done here for function f of x, the result is not going to be a polynomial. You have a new type of function, and this type of function is called a rational function, which makes sense because it has the word ratio in it, ratio like fraction. So technically defined, a rational function is a function that is the quotient of two polynomial functions. And that's what we're going to turn our study to at this point. As we get going, we're going to have to talk about fractions. We're going to have to talk about when fractions are equal to 0 and when fractions are undefined. So let's just review that real quick. A over b as a fraction is equal to 0 if a is equal to 0 and b is not. Okay, so the numerator is equal to 0, but the denominator is not. A over b is undefined if b is equal to 0. Now, why is that really important? Well, as we start to analyze rational functions, one of the things I'm going to have you do first is to make a sign chart. And knowing when your function is equal to 0 and when your function is undefined will help you fill out your sign chart. Okay, so we're going to start talking about analysis of rational functions so that I can draw a quick sketch and understand what the function does. The first step is going to be to make a sign chart. To do that, I need to know what numbers make the fraction 0 or the function 0 and what numbers make the function undefined. In other words, the numbers that have no sign will be the numbers that go on the sign. So let's do a sign chart first for this f that we started with. I'd like to know when this f is 0 and when this f is undefined. So they're both polynomials in the numerator and the denominator, and we know that to find the zeros, we would like to have them factored into their roots. So the numerator can be factored as x minus 2 times x minus 1, and the denominator can be factored as x plus 3 times x minus 1. So f of x is equal to 0 if x is equal to 2, because 2 would make the numerator 0, but not the denominator. I will not put x equals 1 because that makes both numerator and denominator equal to 0. Okay, and I'll say f of x is undefined if x is equal to negative 3 or x is equal to 1, because those two numbers would make the denominator equal to 0. Okay, so now I can make a sign chart for f, which will be helpful later as we gain more and more information about f when we try to sketch the graph. So my numbers on the sign chart are negative 3, 1, and 2. And now let's make a sign chart for f using the factored form of f up here. That's probably the easiest place to do that. So if I use x equals 3, for example, I'm going to get positives all around. So that's going to be a positive. I have to use a number between 1 and 2, so 3 halves, or 1.5 is an example. This will be a negative. This will be a positive, this will be a positive, and this will be a positive. So overall, we'll have a negative. I can use 0 for this interval. This time I'll use red, a negative times a negative, a positive down here, and a negative here. So overall, that gives us a negative. And then I can use any number I want that's less than 3, so negative 10 is suitable. This time I'll use black. So this will give us a negative, this will give us a negative, this will give us a negative, and this will give us a negative. So overall, we'll have a positive. Okay, so at this point, I have a sign chart, and I know when my function is equal to 0. So I can go ahead and plot the 0, which is at 2 comes 0. I have two locations where the function is undefined. I don't know what happens there yet. We'll come back to that. But I can also plot the y-intercept, because that's always an easy point to find. So I can go back to the original function up here and ask myself, what's f of 0? And that'll give me 0 minus 0 plus 2 over 0 plus 2 minus 3. I'm sorry, that should be a 0 there, not a 2. Okay, and that gives me negative 2/3, which is roughly here. Now, I'm going to say this at this point. When we graph any kind of function, if you want more detail, you just plot more dots. I'm going to give you more or less the shortcuts to graphing these things quickly. They might not be as accurate as possible. And if you want more accuracy, just plot a few more dots. Okay, now let's talk about division by zero. That's what we have seen as a reason for our last function being undefined. And there's going to be two different things that can happen when we almost divide by zero on a function's graph. So let's go back. Let's rewrite our function f and talk about it for a second. When we factored it, it was x minus 2 times x minus 1 divided by x plus 3 times x minus 1. And x equals negative 3 and x equals 1 were the quote-unquote problem spots. Okay, so what happens here? If we try to plug in negative 3 for x, we get the following. Okay, f of negative 3 would be negative 5 times negative 4 divided by 0. 20 divided by 0, which you know is undefined. When x is 1, if we try to plug in 1, we will get 0 divided by 0. Also undefined. But now we're going to take a look at what's the difference in what we see on the graph. To do that, we're going to jump to Microsoft Excel and use that to kind of analyze what happens when we almost divide by 0 in these two cases. Okay, so I've opened up a Microsoft Excel spreadsheet, and I'd like you to do the same so you can follow along and be able to do this in class. But what we're going to do is we're going to use the Excel spreadsheet capabilities to explore what happens to our function when x gets close to negative 3 and when x gets close to 1. So we're going to approach negative 3 from the left-hand side of the x-axis. So close to negative 3 would be negative 4. And what we want to do is input values of x that are close to negative 3. And we're going to go up by 1,000th. No real reason, but that'll give us enough data to take a look and see what's happening. So the next value that we would input would be negative 3.999. But I don't want to have to type in all of these values. That would take a while, so I'm going to have Excel do it for us. The way we do that is we use an edit fill, and we're going to ask Excel to fill in a series of numbers. We want the series to appear in a column, not a row. We want the step value to be 0.001, and we want to stop at negative 3. And when I click OK, you should see column A be filled with the values doing what I asked it to do, which is increase by 1,000th each time. Okay, and now in column B, we want to evaluate the function values at these numbers. So I've labeled the function up here in B1, but this doesn't do anything. Mathematically, this is just a label to remind me what f actually is. So let's tell Excel to evaluate the function at these numbers. Excel formulas begin with an equal sign. Since I have a ratio of two objects, I need to put the numerator and the denominator in parentheses. So I'll go ahead and do that right now. Now in the numerator, it says take your x and square it. Our x is negative 4. I could type negative 4, but then I'd have to do that for every cell beneath cell B2, and I don't want to do that. So here's the shortcut. Click on cell A2. We're going to square it. We're going to subtract 3 times cell A2 plus 2. Now we go to the denominator. Select the cell A2, square it, add 2 times cell A2, and subtract 3. We press enter, and we get a value of positive 6. And what we want to do now is tell Excel, okay, you took the cell to the left and used that as the input. I want to do that for every cell beneath cell B2. And the way that's done is by double-clicking on this little blue square in the lower right-hand corner of cell B2. Okay, I double-click and the numbers get filled in. So now we can examine what does this function do when x gets close to negative 3, in this case from the left-hand side. So I'm going to scroll on down and try to observe what happens to these numbers. They seem to be getting bigger. We're now past 7, and I'm going to scroll faster and faster and faster. Past 8, past 9, past 10. And if we scroll all the way to the bottom, the numbers start to get bigger and bigger and bigger. until when we're at 1,000th away from -3, the y value is 5,001. Okay, so these are starting to jump by big increments the closer you get to -3. So in this case, when we almost divide by 0, you'll notice that Excel says, hey, you have an error dividing by 0. The closer we get to -3, the bigger the y values become. The y values start to get massively large. Okay, now let's approach this from the other side. So now I'll start at -2, and I want to get closer to -3 from the right side. So again, we're going to go to a fill. We're going to fill a series in the column. This time we want to go down by 1,000th, so -0.001. We're going down. And I want to stop at -3 once again. Okay, my column A adjusts, and my column B adjusts with it. So again, let's scroll down to the bottom. In this case, they're all negative, and these numbers once again start to get very large the closer you get to -3. So on one side of -3, the graph starts to spike upward, and on the other side, the graph starts to spike downward. We'll come back to this in a few minutes. But first, let's take a look at what happens close to x equals 1. So let's type in a 1 here in cell A2. And again, let's do a fill series. Okay, fill series. Let's approach 1 from numbers less than 1. Oh, I beg your pardon. We've got to start close to 1. So let's start at 0 and get closer. So fill a series in a column. We're going to go up by increments of 1,000th, stopping at 1. Okay? Column A adjusts, column B adjusts with it. All right, now let's slide on down and see what happens to our y values here. They're negative, they're just getting smaller, but they don't seem to be getting to be very big, large, or very big positive, very big negative. In this case, they seem to be centering around a certain number. And at this point, it's -0.25. And maybe if we went closer to 1, we'd get closer and closer to a certain number. Okay, we're going to hold off on that for the moment, but I'm going to notice that this does not get very large, big, or very large, very large positive, very large negative. This number seems to be stabilizing. So this is a different case of dividing by 0. All right, let's take a look at one more, and let's get closer to 1 from the right side. Okay, in a column, we're going down by 1,000th, and we're going to stop at 1. Column A adjusts, column B adjusts with it. Okay, scroll on down. Now these numbers are getting larger. They're negative. Or I should say they're getting larger in absolute value, but they're not getting huge. And again, they seem to be centering around a certain number. I'm not sure what that number is, but in this case, they're getting closer to -0.24 something. All right, so now let's return to our notebook file and talk about what we observed the 2 times we tried to divide by 0. Okay, so let's write down some observations here about what we saw in the Excel spreadsheet. And I'm going to introduce some notation that you might have seen before, but might be new. So let's first look at when x was close to -3. Okay, we did 2 different things. We let x approach -3, but be a little less than -3. So this little notation here with a minus sign above the -3 tells us numbers that are smaller than -3, but close. Okay. Now, what occurred in the Excel spreadsheet? Okay, the y value got very large. It approached positive infinity. We also looked at numbers that were close to -3 but bigger. So you would write that as x approaches -3 with a little plus sign above the 3, a superscript. Okay, what happened in that case? Okay, f of x approached negative infinity. Okay, this feature is called a vertical asymptote. It means the y values get very, very large the closer you get to this number, in this case -3, and they can be very large positive or very large negative. We'll take a look at what that looks like on the graph in a second. Vertical asymptotes will always occur when we divide by 0 and it looks like number divided by 0, okay, number that's not 0. So 20 over 0, 6 over 0, 13 over 0 will always produce a vertical asymptote. I don't have to do much more analysis than that. Now I have to analyze what happens on either side, whether it's positive or negative, but I'll know it's a vertical asymptote if it's number divided by 0. The 0 over 0 is more interesting because this could produce a number of different things. In our case, the one we looked at x approaching 1 from the left and x approaching 1 from the right. And what happened? Our numbers seem to get closer and closer to this magic number, and I'm going to go ahead and show you that that magic number was -1/4. Okay, but in this case, you don't have the numbers spiking up or down massively. The numbers are getting closer and closer to a certain value. And when that occurs, we have a feature that's called a removable discontinuity. And another word for that you've probably used before is a hole. So let's go back to our picture now and talk about what we can add to the graph that makes this more clear. Okay? We said that at -3, we have a problem. The function's undefined, right? And I'm going to go ahead and draw a dotted vertical line at -3 to show us there is no y value at that spot. Okay? That's where we tried to divide by 0. We're not allowed to divide by 0. And around that place, we saw some interesting behavior. As you got closer to -3, the y values spiked upward. So the closer I got to this barrier, the graph headed toward positive infinity. Okay? So we can draw that by getting very skinny the closer we get to -3. Now, I want to point out that this also matches up with my sign chart, which says that my function should be positive when x is less than -3, and it is. Also, the sign chart says on the other side of -3, my function should be negative. And as x approached -3, from the right side, the y values approach negative infinity. So I can draw that by getting skinny, closer I get to -3, and having the y values shoot downward. Okay, so this is more or less what you're going to see when we talk about vertical asymptotes. Y values shooting upward or downward very fast the closer you get to this x value. Now, when x was getting close to 1, we saw something different. We saw the y values getting close to -1/4. But there is no dot at x equals 1 because the function's undefined. Okay, so what you're going to see there, if you were to zoom in close enough, is you would see an open circle at 1, -1/4. And then the graph would go towards that dot, skip over it, and then continue on. Okay, that's what's meant by a removable discontinuity. If I could fill that hole, then I would no longer have a problem. I would have a continuous graph that just goes smoothly on through x equals 1. But because of the division by 0, we have a hole there instead. Okay, so now I can look back at my sign chart and more or less fill in the rest of the graph, with the exception of the end behavior, which we're not going to talk about today. So what happens after x equals 1? The function is negative, right, until it gets to 2. That's where the 0 is. That's what we have on our graph. We know it's going to pass through 2 because of our sign chart, so it becomes positive after this. Okay, I don't know what happens after that. Until next time, we'll talk more about that. Before x equals 1, my function's negative until we get to that asymptote. Okay, so if I'm going to clean this up a little bit, all right, I might erase this part of the graph here, knowing that from the right-hand side here, I have to pass through 0, -1/4, and then my asymptote shoots down towards negative infinity. And for now, we're going to leave the end behavior as a question mark until next class, and we'll talk about that in more detail. Okay, so this may seem a little bit unsatisfying to you at the moment because I'm not giving you all the steps to doing a rational function, and I understand that, but we're giving you this in pieces because there's a lot to consider here. So far, we've done a sign chart, we've looked at the zeros, and then we've looked at the division by 0. Let's talk about the division by 0 one more time here. So in our case, we had two different issues here. We had the number divided by 0, which produced the vertical asymptote. The sign chart helps me tell what kind of vertical asymptote I'm going to have. Now, what about this 0 over 0 problem? Okay, I've said the y value was getting close to -1/4. Okay, now how did I know that? The spreadsheet helped me guess that, but is there a way that we can do that with work on a piece of paper that tells us that? And the answer is yes, actually. So if we go back to our f, okay, our f of x was equal to, when I factored it, x minus 2 times x minus 1 divided by x plus 3 times x minus 1. Now, if I look at this, I'm going to notice that the numerator and the denominator share a common factor of x minus 1. And that's the reason why this was coming out to be 0 over 0 if I tried plugging in 1. Okay? So it's tempting to just cancel out the x minus 1's in the numerator and the denominator, right? Because you do that with numbers all the time. Problem is, if I do that, I'll lose the fact that x can't be 1. Okay? So what I want to do here is I want to make a note. I say, okay, as long as x does not equal 1, okay, then I can cross off these x minus 1s. And my function f is now equal to x minus 2 over x minus 3 for every x value except x equals 1. All right? So I keep this in mind because I'm going to have to say something about this in a second here. Now, I know there's no dot on the graph of f at x equals 1. But what I can do here is I can say I could almost plug in 1. So I'm going to write as x approaches 1, and I'm going to try to plug it into what's left of f here. Okay? In other words, if I could plug in 1 into f, what would I get out? And you're going to notice I'm going to get a negative 1 in the numerator, a negative 1 in the numerator, and a 4 in the denominator. And so that allows me to know where the hole occurs. So I made a note, x could not equal 1. I removed the 0 over 0 problem. And then I plugged in the 1 to show me where the graph would be going if I could plug in 1. So there is a way to tell where the hole goes. For our purposes, this is basically how I would handle analyzing a rational function. And if you remember RADI from last year, this is basically the same steps, just presented a little bit differently. So number 1, we made the sign chart for our rational function. From that, we could plot the zeros. And then I said, go ahead and plot the y-intercept while you're there. If you were experiencing any division by 0, you needed to analyze whether that was going to be asymptote or hole, removable discontinuity. So I could plot those on the graph. And then I would say go ahead and plot any extra dots that you need to gain more detail. Because these are not quite like polynomials, they're not necessarily smooth and have no breaks in them. They're going to have different features. And then next class, we'll talk more about, okay, what happens at positive or negative infinity with these guys, the end behavior. Now, before we leave, let's just go ahead and quickly do one more example and get as much detail as I can give you before doing end behavior. So, step 1 was to get a sign chart for our function. So I do that by factoring numerator and denominator if possible. Numerator factors nicely, and denominator factors nicely as well. So I notice that f of x will equal 0. Actually, I don't see that at all because the number that makes the numerator 0 would also make the denominator 0. So f has no zeros. F has no zeros. But f is undefined at plus and minus 2 because the denominator is 0 at those two values. Okay, so my sign chart for f would contain those two numbers, negative 2 and 2. And my analysis will say, let's see here, the numerator will always be positive because it's being squared, except at negative 2. And if I use 10 for x, then the denominators are positive, so we get positive. If I use 0, the numerator is positive, the denominator is a negative times a positive, so overall negative. And if I use negative 30, I'll have a positive divided by a negative times a negative, so a positive. I'm going to go ahead and get a preliminary sketch of my graph here. Now I have no zeros. I can get a y-intercept by plugging in 0 for x up here, and I'll get that f of 0 is equal to minus 1. So right here. Now let's analyze the 0 divided by 0 issues here. There are two places to look, x equals minus 2 and x equals 2. If I use negative 2, I'm going to get 0 divided by 0, which means I have to do a little bit more work to find out what happens. So I look at my f, and I say for x not equal to negative 2, f of x is the same thing as what would happen if I canceled an x plus 2 and an x plus 2? Well, what would be left is x plus 2 divided by x minus 2. So this function here is the same as the original f, except that this place x equals -2. Okay, well, what if I could plug in -2 or numbers close to it? Okay, well, I'm going to do that, and I'm going to see that f of x would approach 0 divided by -4, which is 0. Okay, so this is a hole. And the hole is at -2, comma 0. So right here, I'm going to put an open circle. Gets very close to the x-axis, but doesn't actually touch the x-axis. Now when x equals 2, I'm going to get 16, 4 squared, right, divided by 0. Okay, that is every time going to be a vertical asymptote when it's a number divided by 0, and that number is not 0 in the numerator. Okay, so that tells me at 2, I'm going to have a vertical asymptote. Go ahead and draw on that dotted line. The sign chart now will help you determine what happens on either side of that asymptote. To the right of 2, positive. So that means I need to come from the north, right? My y values need to get very large as I get closer to positive 2. Okay, and I'm going to leave the rest of that a question mark for now. On the other side of -2, the sign chart says negative. Okay, so I'm going to shoot down the closer I get to positive 2 from the left. All right, now I have to pass through 0, -1, the y-intercept. I have to go through or go to the removable discontinuity. On the other side of the hole, we're going to be positive. So we're going to come up, and then from there I'm going to say question mark, and we'll come back to that next class. So right now you're plotting, or you're able to plot kind of what's happening in Houston, Texas, in the middle of the United States. Next class we'll take a look at what happens on the east and on the west, the end behavior.